Let us begin today's session. Session for smart grid, basic to advanced technology. Week 9, 10th, and remaining 4 weeks. Hybrid AC-DC microgrid. So we'll not go through this, but we'll go through these demonstration part of these solar power, wind power, battery. Hardware in loop. All these things we can do. Is this slide visible?
Yes, sir, visual.
Okay. Yeah, so let us begin with demonstration of the solar power generation. So for hardware in loop, we use all these power amplifier, and there are some digital simulators, real-time digital simulator. One of them is this Opel RT. So RT is for real time, and one is RTDS. So this we will come across in maybe next week, next to next week. So this is real-time digital simulator, and it has a software also, RSCAD, just like PSCAD. Have you heard of PSCAD software? Anyone? So why do we use this RT, Opel RT or RTDS? Can anyone of you tell why we need these simulators? Anyone? So we want to whatever algorithm, whatever things, whatever we have made proposals that we want to test on a real system, but we cannot go to a distribution system and put our algorithm there or our charger which we have created. We cannot do that. Or we cannot go to a transmission system line and connect our PV generation there directly to perform the study. So we have to perform the study before the connection, actual connection. So for that, because we cannot connect to the actual system, but we need to do the study on an actual system, which is not actual, but it should work as the actual. It should mimic that actual. So for that, we have created these real-time simulators, which will they are very fast. Their time step is with microseconds. So it's as if everything is happening in real time. So if we change something, we can observe the output impact of that change within few milliseconds or microseconds. So that is the benefit of using these real-time digital simulator, and that is why we are using. Is the slide in PowerPoint in slide should show mode or is some problem?
Slide, sir, slide not changing. It is first
Slide is
slide.
not changing. Let me share again. Now is it changing?
Yes, sir. It is showing demonstration and then live session.
I don't know why it is not showing in slideshow mode. I'm doing slideshow, but it is not showing slideshow. Okay, let's do it in read mode. Now slides are changing, right?
Yes, sir.
Okay. So I was saying, why are we using these real-time digital simulators? Because we want to see how the things are working on actual system, but we cannot actually do connect new generation or whatever equipment we want to test on the actual system. So before actually installing any big renewable plant or even installing any kind of relay or PMUs, we have to first of all do a study. So we do simulations. We use different types of simulators. PSCAD is one of them. RTDS is another one. So we will make the actual physical system. We will make inside that simulator, and that actual system will be mimicked by that simulator. So that simulator will work as a that as uh, that that actual system. So here the simulator grid emulator is emulating the grid. It is behaving like the grid. It is not actual distribution grid. but it is behaving like a grid. So we are using this grid emulator to mimic the grid. Similarly, here the demonstration is for solar power generation, and we don't have in the lab, we don't have the actual PV system, PV panel. So for mimicking the PV, we have used this programmable DC source. So whatever characteristics a PV system has, what is happening today? Sorry for the disturbance. We'll have to work like this only today. So we have different PV characteristics, right? We have this PV and IV characteristics.
Not changing, sir.
Can is it not visible? What I'm writing something. I'm drawing this PV and IV characteristics. Is it visible?
No, sir. On the screen, it is demonstration of solar power generation.
Yeah, I'm on that slide only, but I'm drawing something. Can you see that? Sorry.
No, sir.
Can you see what I'm drawing something? What about others? Yes, others are able to see.
No, sir, it's not changing. Only the labs settings it shows.
No, I'm not changing. I'm drawing something. Are you able to see what I'm drawing? I'm
Yes,
drawing.
sir, it's visible. Yeah, it's visible, sir.
Yeah. So I was just drawing. I don't. Today there is some problem. I'm not able to do this full slideshow mode. I don't know what's the problem. So we'll have to do like this only. Yeah. So I was saying this is the PV source, not the actual PV source, but we are trying to emulate the PV source using a programmable DC source. So this DC source will provide these PV and IV characteristics. Just as a solar PV performs, this will also act like a PV source. And then we are connecting this PV source to the grid. So it is a DC source and grid is AC. And we are using this inverter. So this is a black. This is a three-phase inverter. So we have a PV panel which we are modeling. We are trying to mimic that using a programmable DC source, and then we want to connect it to the grid. So grid is not actual grid here. We have a grid emulator which is behaving like a grid. Then this is the converter in between, which will convert DC into AC, and to develop its control logic to extract the maximum power, we have to perform, we have to make control loops. So for that we need to sense the voltage and current. So for this we need sensors. So we will sense the voltage and current. And this control logic, so grid is mimicked using grid emulator, source using programmable DC source, and this controller is the control logic is developed inside the OpenRT hardware. And this converter is a physical device which is IGBT stack. It's a actual it's a actual converter. This is the actual converter. Okay, this is the load, and we are OpenRT is inside this system. Means OpenRT is linked with MATLAB. So OpenRT is also a hardware where we can give inputs and take outputs also, but we can program the control logic inside the MATLAB, and MATLAB can interface with that OpenRT. So whatever control logic that we write, MPPT algorithm, P and O, or whatever algorithm is there for MPPT, if we write it in MATLAB, same will be implemented on the OpenRT. And so here we will give the input output of this programmable DC source to the actual IGBT stack. But to extract maximum power from that inverter, we need to give firing pulses because there are switches, and to extract the maximum power we need to give appropriate firing pulses. Those firing pulses are generated by OpenRT. Is it clear? Is it clear? Am I audible? So this inverter can be of, or the converter can be of two types: single stage or two stage. So this is example of single stage solar inverter. Then there can be two stage. Single stage means directly the DC is converted into AC. So here we have PV panel, and directly DC will be converted into AC in a single stage. So what is the advantage of single stage? Can you tell? Yes.
Losses are reduced, sir,
Yes, correct.
because
Losses.
of so many conversions. It has low losses.
Correct. So earlier we were having this DC DC and DC AC conversion stage. So this was the boost converter or a boost converter, and then the output of converter would go to this inverter, and it will generate the three-phase signal. Here we have more switches, more conversion stages, so efficiency will be less. So losses are more because more conduction losses, more switches, more switching losses, and that is why earlier whatever converters we were having, they were two stage. Then later we shifted to this single stage. So these are the single stage inverters. So here we have three.
But voltage of DC generation is very less as compared to AC. So then the transformer around they are required, na?
Yes, that is why in two stage we use this boost converter first.
Practically, directly conversion of DC to AC, once our grid is high voltage, it is impossible.
Yes, that is correct. So we have seen in I think in week 3 when we were discussing that solar. So I had shown one layout for wind. So for solar farm. So there are initially suppose it is generating 415. So all there will be strings. They will be combined together at a particular. Then again at a low level they will be converted into AC. Then transformer will be there. Then it will be stepped up. So there will be 2 3 stages. Finally it will go to 230, 132 kV. So it is not that initially it is converted into AC, then we have to use transformer. Without transformer we cannot do. You are correct. So because single PV, even single panel, it has the voltage a single panel can produce is limited. It is less. So we convert these panels into series parallel combination to increase the voltage and current ratings. So once we achieve a good amount of DC voltage, then we will convert that into AC and then we will use several such parallel connections and use one transformer. And then there will be such small transformers. Again, they will be in parallel, several transformers will be in parallel. Suppose the rating of the plant is 5 MVA, 5 megawatt. So 5 MVA transformer is being used or that at the top level. So below that 5 MVA, there can be 5 1 MVA converters. So all they will convert DC into AC. Then we'll be using another big transformer. So we need transformers to to boost the voltage, to step up the voltage. So in this example also this case study, mm, because that IGBT stack which has been used, that inverter has 4 legs. So this is one IGBT module which has 2 switches. So 4 such modules are used. So we have 4 switches. So 4 legs. So 4 3 phase it will become 4 wire. But in example only 3 phase has been considered. It's a 3 phase 3 wire system has been considered. So one leg is not used. So there are only 3 phases. One leg is used for boosting the voltage. So this one leg, this here neutral point, this is taken out, and here we have diode also. And here we have PV panel. So this leg will act as a boost converter. And then the remaining 3 together will be acting as an inverter. We also have here one DC link capacitor is also there. Okay, so and across this DC link capacitor there are resistors. So two capacitors are connected in series, and across them there is in parallel there is a resistance. So why do we use this resistance? Can you tell? And what this resistance is called? So these are called bleeder resistance. So when we cut ourselves, let's say our finger is cut by knife, so we bleed. So blood is lost. So similarly, this capacitor, the energy stored inside this capacitor when the inverter is not in use, then also there is some energy stored in the capacitor. So for safety purposes, if someone touches that equipment and if energy is still stored within the capacitor, one can get shock. So that energy, stored energy, is released or it is dissipated in these resistances. So they are called bleeder resistances. So these resistances are used to dissipate the energy stored in the capacitor when the system is not in use. Similarly, across each leg also there is one capacitor. So we call it, across each leg also we have a snubber circuit. So what is the use of snubber circuit? Can you tell?
It will limit the voltage.
Correct, because yes, because capacitor, what is the nature of capacitor? It won't allow sudden change in voltage, right? Because I is C dV by dt. So the capacitor, it's the property of capacitor that it will not allow sudden changes in voltage. Similarly, inductor doesn't allow sudden changes in current. So it will. So that's why we have this capacitor in parallel with in parallel with each leg. So this capacitor will provide this. This is also called snubber circuit. So it will provide dV by dt protection against high dV by dV rates, high rate of change of voltages. So these are the two important things here. Now we will see that these single stage and two stage. So in single stage we have three control loops. So here you can see three control loops. Can you name what are the three control loops here? So these are written here. So first one is this, second one is this, and third one is this. So this is the first one is MPPT control loop. So it will extract maximum power for the given temperature and irradiance level. So these IPV and VPV are coming from the solar panel. So these input, and it will generate a reference for the DC link, which is input of the inverter. So thing. So the input of the inverter is this DC link capacitor. So what should be the voltage of this capacitor, voltage rating of this capacitor for power to flow from DC to AC side. Is there any criteria for that? This much should be the voltage so that power flow can happen. How power will flow?
by power angle, sir. But in
Power
DC,
angle.
where is angle?
They are saying the difference in angle will result in power flow. Yes,
But in DC,
yeah, but here we have DC.
So VDC is always greater than VAC.
Yeah, but so it should be sufficiently large. So this voltage difference will enable power flow, transfer of power from DC side to AC side. So this voltage VDC should be greater than the peak value. So this is VRMS. So peak value, so it will be root 2. So this VDC should be at least, it should be greater than this much, root 2 VAC. So means peak value of the AC side, AC. So if the if volt AC side is 415 RMS, then peak value is 586 volts. So in the example, 700 volts has been considered as the this rating of the DC link capacitor. So even for 100 volts RMS, you can take 400. It's sufficient. It should be, there must be sufficient gap so that we can have power flow, sufficient power flow from DC to AC side. If the voltage difference is not there, power will not flow. So that is one important point. So, so and that will decide this. So MPPT will decide the reference for VDC link, and the actual DC voltage is provided. We can measure that, and then this DC link voltage control will try to keep this actual voltage close to the reference. So it will try to maintain the VDC at the reference value. And this voltage control loop again generates this ID star. So all this control is happening in DQ frame of reference. So we have three frame of references. One is phase domain. Phase one is ABC. The ABC domain, or we can say frame of reference. Then we have alpha beta 0 frame of reference, and then DQ0 frame of reference. So alpha beta is also called stationary frame of reference, and this is called synchronously rotating frame of reference, DQ0. And for this DQ0 we need one information, which is theta. So here we are converting currents and voltages into DQ domain.
So
Voltage.
sir, what is this first time I am hearing this alpha, beta, 0 and DQ 0 domain?
So whatever control we are doing, everything. So okay, let me start with that. First of all, why are we converting? Why are we moving to these frame of references? We have analog signals, voltage and current, right? Voltage and current, three phase quantities, and these are sinusoids. Correct? We can operate with sinusoids also, but the simplest controller which is available and which is most widely used is PI controller. So if we give a sinusoidal input to PI controller, then tuning it to maintaining, tracking the references requires a very cumbersome controller design for PI controller. The design becomes very cumbersome. It will become a to even second or third order system. We can do that. So there are some converter called as proportional resonant converters. So it's a extension of PI converter only, PI controllers. So with sinusoid, we have to use these PR controllers if we want to track the reference. If we use a normal PI controller with these sinusoids, there will be large error, steady state error. That we don't want because we want to track the reference. So PI works well with the DC quantities, DC signals. So whatever control theory which we have studied with PI, we have used these DC signals for PI controllers. The input were always DC, not sinusoids. Because PI is very simple, cheaper, and also robust, so we want to use PI. But we want to avoid this cumbersome design also. We want a simple controller also. So that is why what we do is we convert this ABC sinusoids into another quantities. So there is a frame of reference which convert this ABC quantities into other quantities. So there are two options in that. One is stationary frame, which is alpha beta, also called as alpha beta frame. So ABC will be converted into alpha beta 0 quantities. So we'll get for ABC corresponding alpha beta 0, three values. Similarly, there is another option which is DQ0. Here also we'll get three values and it will be combination of all these three ABC values. Just as we have already studied one frame of reference, that is sequence transformation. Uh, Sequence component. Have you heard of this? We use this in short circuit analysis, fault analysis.
Positive sequence and negative sequence.
Yes, correct. So we convert ABC into one, or let's say if it is VABC, so we convert into V120, positive, negative, and zero sequence. So this is also a conversion, a transformation to another frame. So this is sequence frame of reference. Sequence domain. This is phase domain. So here also we are transforming to make our life simple. Because in ABC, doing three-phase short circuit analysis is very complicated. So we are converting it into phase sequence domain. So we get three different. So we can do analysis, the same analysis which we were doing on single phase. If it is a balanced system, we do per phase analysis. So here we get three balanced systems. Positive positive sequence, we can draw one circuit. Negative sequence, we can draw another circuit. Zero sequence, we can draw another circuit, and then we can combine them to get the overall effect. Similarly, here also we are converting this ABC into another frame of reference to get, here we have sinusoid. The stationary will also give you sinusoid. So that is why we are not using alpha beta 0. But DQ will give you DC quantities. So we are using DQ transformation for the control. So here that is why you are seeing ID star. So this is, so current ABC is converted into IDQ0, and this, so we have three quantities here, ID, IQ and I0. So this is ID star. So it is a reference value which this control loop will generate. And then it will be compared with this measured. The output of this converter will be IABC. That will be converted into IDQ0, and that will go here. And we can compare this ID star with that ID. Similarly, third, okay, this is second. third and one more. This is the fourth control loop, which is the PLL. So this theta, which is required for converting ABC into DQ domain, is given by this PLL. So PLL will lock with the frequency of the grid. So because we are saying suppose one train is moving and you are sitting in another train. Both train are moving at the same speed. So you can see person in that train, you will see that you both are sitting. Means there is no relative speed, right? You will see as if that's just another compartment. You are sitting together. It's like that. That is why it is called stationary. There is no relative speed. So actual phasor and this reference frame phasor both are moving at the same speed. Then we can get these constant quantities. But how to ensure that speed? How to know that speed? So that angle, that speed, that omega is calculated by this PLL. So if this DQ frame of reference also rotates at the same speed as the grid voltage and current signals, so at the same frequency as the grid frequency, then we can get these DC quantities. So for that we need this angle information, and this angle information is provided by this PLL. The PLL DC, the point of common coupling, whatever voltage is there, that voltage will be the input for the phase locked loop, and it will provide us this theta, which will be used to convert ABC into DQ quantities. DQ quantities. So is it clear? Is it clear?
Yes, sir. Understood, sir.
Okay. So let us move ahead to cover today. So this is dual stage. Then single stage we have seen, and here we have two stages. So here first stage will be DC to DC conversion. Here again in first stage, in single stage MPPT and inversion both will be done by same converter, but here DCAC converter will do the MPPT. So it will be generally it is boost or buck boost converter. So MPPT voltage control, DC current control. This is inner current control loop, so it's a slower, and then DC to AC converter. So output of this will be to a DC link. DC link. Then here we'll be having an inverter, DC to AC. So the voltage of this DC link capacitor has to be maintained. So that is why this DC link voltage control, then same AC current control loop and PLL. So here we have three loops, current control loops. Here also we have three loops, 1, 2, 3. So in single stage we are having only 4 loops. So here we are having 6 loops, we can say. So it is done bleeder since we have done covered. So let us move to wind demonstration of wind power generation. So this also we have already seen. So kinetic energy will rotate the turbine gearbox because the speed is less. So we have to increase the speed so that speed should be sufficient for the generator to generate power. So then this is a variable power we have to It can be it's a variable speed output, because here wind turbine speed is different. We want to convert it into fixed frequency, so we need power converters for that, and then we use transformer and connect it to the power grid. So this is the system for laboratory demonstration setup for the wind power generator. So here we have the DFIG has been considered here. What is full form of DFIG?
Double cage induction motor.
No, not.
It is induction generator, sir.
It's a
Doubly fed induction.
doubly fed induction generator. So both we can, the supply is both rotor and stator are fed. It is doubly fed. So rotor can also receive power. It can also, it's bidirectional power flow in rotor and stator only in one direction. That will supply. चल. Okay, so we have this DFIG, and this is for DFIG. So here this is the DFIG generator, and the input here is the turbine. So in lab we can have this DFIG, but what will be the turbine? How to get the turbine in lab? So for that, what we are doing? So DFIG emulator. So wind emulator we can see here. I think, oh, that picture is not here. So it is implemented in this Vivect FPGA. So these characteristics of wind that we see different at different wind speed, we have different characteristics. So these characteristics are modeled in this using this FPGA. We can program it. And the prime mover, the turbine which is rotating, so that is this. We have a DC. We have a DC motor here, and this is an induction motor. We can control this DC motor to act like a turbine. So we can control it because this is DC, so we can control it using a chopper, which is a DC-DC converter. And how should we control it? So that we need to vary its duty cycle, and that will of the converter. So how the duty cycle should be vary? That will be decided by this algorithm which is inside the FPGA controller. So from all these setup we can see these are not actual. We don't have actual wind turbine here. We don't have actual wind DFIG generator also. But we are trying to use whatever we have. DC motor we have different hardware, and we have different simulators. So we are trying to generate those characteristics using these different types of simulators. So we can feed these characteristics, we can code them, program them, so they will behave like that. So this DC motor will behave like a turbine. So we have to control the chopper in such a way that it can behave like a turbine. So it will give same type of wind characteristics, speed torque characteristics that we want to achieve. So this DFIG is emulated in this way. Then the So this we have emulated. After that we have this converter, right? So this converter is here, this back-to-back converter. So one is the grid side converter and another is the rotor side converter. So we have two converters on the rotor side. So one is rotor side and this is grid side converter. In between we have a DC link. And this is also connected. Rotor, and this is connected to stator, and then we have a grid here. So in between we have this converter. So this converter also we have to control so that we can extract maximum power and then feed the power. Because actual wind turbine has to operate for several different wind speeds. So DFIG can allow that. We can operate in sub-synchronous speed, at synchronous speed, or above synchronous speed. So if the rotor speed is less than synchronous speed, is it sub-synchronous, super synchronous, or synchronous? So we have these.
Subsynchronous.
Yes, so we have three cases. One is this is sub-synchronous, speed is less than synchronous speed, and this is synchronous, and this is super synchronous. So we can operate using DFIG in all the three cases. And based upon the operation, these three modes, whether the rotor will supply or rotor will consume power, that will be determined. So if the rotor is operating at sub synchronous speed, then the rotor will take power from the grid and stator will feed power. If it is super synchronous, both will feed power. And if it is synchronous, rotor will not consume any power from the grid. Only synchro stator will provide. So that is why these converters are bidirectional. So these are the control for the grid side converter and rotor side converter. So we have these two converter, back-to-back converter. This is this is rotor side connected to machine, and this is connected to grid, so it is called grid side converter. So main aim of grid side converter is to maintain this DC link voltage. And rotor side converter, what it will do, it will try to extract the maximum power. It will try to operate the turbine at the MPPT point to feed maximum power into the grid. So that is why here we can see this is the MPPT algorithm. Here perturb and observe algorithm has been used. Another algorithm are this incremental conductance. So wind velocity is the input for this block, then it will generate a reference speed which will compare with the rotor speed, and then there is PI controller. So here also the control is in DQ frame of reference. So whatever control we are doing, it will always be in DQ frame. That is why you can see here it is ID star, IQ star. If you want to inject reactive power, then we have to provide this reference for IQ star. So finally these signal will be generated. and for PWM generation, and these 6 pulses will be generated, which will control the rotor side converter, and these 6 pulses will be generated for controlling the grid side converter. So the aim of the controller is to generate these pulses so that the switches will switch in a particular fashion to achieve the desired goal, to track these references which you want to. So current reference, reference speed, reference frequency, reactive current reference, all these, and DC link voltage, so all these should be at their reference value. So is this clear? Okay, so next is battery management system.
Sir, why you are not using in W for the synchronous generator instead of induction generator?
Doubly fed synchronous generator. I have not.
Means synchronous generator, sir, alternator in place of induction generator.
Another option for this. So there are four type of generators for this wind generation system: type 1, type 2, type 3, type 4. So DA5G comes under type 3, and type 4 is this permanent magnet synchronous generator, PMSG.
Okay, sir.
So that we are using for type 4.
We can also use, sir, DC generator.
DC generator, and I don't use really, because induction generator are very robust.
Yes, sir.
Induction, that is why generally we use induction motor only. So next is battery management system. So in this, so we these are the main function of VMS. One is the monitoring of all the parameters. So we want to know all the parameters. What is the state of charge? What is state of health of the battery? So these are the online estimation of state of charge, state of health, and we want to monitor voltage, current, and temperature for each cell for thermal management, for balancing. So for thermal management, we need all these things. Then cell and module balancing is the another function. So by monitoring these, we want to maintain the voltages or SOC same across all the cells to avoid any kind of thermal runaway, hotspot generation, any kind of what we call mm, circulating currents. All these things we want to avoid. So for that we need cell module balancing. So these are active, passive. This also we have seen. So this ninth week is for demonstrating this active and passive balancing, cell balancing. Then another is to compute energy and power limit of the battery. If we do not do these cell balancing, then it will degrade the life of the battery. That is problem. So we want to avoid it, and for that there are two balancing techniques. One is passive balancing, another is the active balancing. So in passive balancing, in demonstration, three cells were considered, three lithium-ion cells, and there is one already existing passive IC, passive balancer IC. So three cells connected in series. One cell is 3.7 volt. So together they will give a volt, 11.1 volt. So they are connected in series. So these balancer ICs, they also have protection against short circuit, overload, over discharge, and charge. Over discharge and charge also we should always protect, because the battery life depends upon the depth of discharge as well as the discharge rate. More the depth of discharge and more the discharge rate, what will happen if discharge rate is quite high? Should the depth of discharge be high or low for good battery life?
Should be low, sir.
Oh, low.
Depth of discharge is should be low? No, think carefully once again. It's not as state of charge, it is depth of discharge. So we had seen in, I think in previous weeks, there is a relationship between depth of discharge, number of cycle, and discharge rate also. So as the depth of discharge increases, the number of cycles reduces. The battery life reduces. The depth of discharge should be, sorry, correct. You were all correct. Depth of discharge should be low. We don't want high depth of discharge. If it is high, then correct, it will degrade. So depth of discharge should be low. Then we can increase the battery life. So here also, to do this passive balancing on DC, so balancing during both charging and discharging has to be done. So for charging, one DC power supply is considered, and for discharging, so it is a rheostat is considered. So it will act as a load. So it will discharge the battery. So this balancer IC will try to maintain the same voltage across all the cells. So there are inside this IC there are these four switches, four MOSFET. So for charging, MOSFET 1 and 2 are activated. And for discharging, MOSFET 3 and 4 activated. So if there is some cell which is having higher voltage, so it will be that voltage will be depleted, to ensure that all the cell voltages are same as 2.4 voltage. Here also, if one voltage for one cell is more, so that resistance which is connected across that switch, the charge will go into that and the voltage will again come to, it will equalize. So for charging, because we do not want the voltage to go beyond a certain limit, so as soon as it reaches 4.2 volts, the protection circuit will be activated and it will stop the charging. And similarly, with the voltage should not fall below certain value, which is 2.4 volt. So here also, as the voltage reaches this value, protection IC will stop this. It will stop the discharging process. So what is the disadvantage for passive balancing in this case? Can you point out any disadvantage here?
Losses will occur.
How?
You are balancing by adding resistors.
Yes, correct. So because we are using resistance here for equalizing the voltages, because battery current is taking a resistive path, so I square R losses will be the heat dissipation. That is going to deteriorate the capacity of battery, because temperature will increase. It may increase the temperature to very high value and it can lead to thermal runaway. So passive balancing, although it is very easy and it is cheaper, but because it increases the losses, is not used for very large modules. So that is the disadvantage. So active balancing is used. And this was a setup for active balancing where CHIL hardware is used. CHIL hardware setup. What is the full form of CHIL? Do you remember? One is PHIL and one is CHIL. This is called power hardware in loop. So for this we need power amplifiers. So what is the full form similarly? CHIL. What is C here? HIL and L. So H, I and L both are same here. But here it is P, it is C. What is C here?
Current, maybe.
Not current.
Charge,
No. One more guess. So what are we trying to
capacity,
validate here? No, I will give you a hint. What are we trying to validate here?
capacity,
No, no. We are trying to develop some logic, right? Control logic. That we want to validate. So early power hardware in loop. What did I say about power hardware in loop? That if you want to test our system or whatever new thing we want to implement on a big and actual distribution or transmission grid, then we have to model that. We cannot do it on actual system, so we model it. So we have a network model and we do everything on that. And to we can even take input from some actual hardware system. Suppose uh, I have a distribution system and I want to integrate, just as we saw one case study in for that optimal storage siting, right? So IITR distribution grid. So that was modeled inside. It was modeled inside the RTDS. So inside RTDS, I have the model of IITR distribution system. It is not the actual distribution system, but it is a model which will behave like the actual distribution system. So now, what I want to know the optimal nodes or buses where the storage should be connected. So I did the simulation. I ran OPF and found that at bus 5, 9 and 12 at these four locations the storage should be connected. Okay. So this I found out using simulation. Now I want to find out if actual battery storage is there, what will happen? Results should match. So what we can do at that particular node, at these four nodes, let us consider only one of them. So our system is inside RTDS. So this is distribution grid, and so because I can provide, let's say this side, these are output pins and these are input pins. Now, suppose let's say this pin corresponds to this bus number 5, voltage of bus number 5. So at bus 5, what I can do here, I can connect that storage, the actual storage also, or storage emulator. Let's say it is a storage emulator, which will behave like the actual storage. So I can connect that storage at this bus in that model. So this storage is behaving like actual storage. But this storage which is behaving like actual storage will give voltage and current at a very high value, right? 10 ampere, let's say, maybe 50 ampere, 15 ampere to 20 volts. But this RTDS can take input only within plus minus 5 volts. Now we need to scale these. In between we need some interface. So these are called power amplifiers. So it will amplify this 5 volts to 220 volts. And vice versa also 220 volts to 5 volts. So we can give this 5 volt inside, and then also we can take output. So we can charge the battery. So here means through power amplifier itself. So it can discharge and charge. So this is power hardware in loop. So we are working with high voltages. So we have power amplifier. We need power amplifier for that. If we remove the power amplifier, then it will become a. And here also, if storage is also modeled using some similar to RTDS, some simulator is there, then it will become a software in loop. Let's say I model the storage in MATLAB, and it will become a storage in software in loop. Now, see here is controller hardware in loop. So we are doing active balancing, and we want to see the control logic which we have developed for active balancing. Is it working fine or not? So that I want to check. So here the control logic is developed. The system is inside OpenRT here. Just like distribution system, ITR distribution system was inside RTDS or RSCAD, that these three modules, battery cells, are inside OpenRT. So this is their model. So these are modeled inside the OpenRT. And from OpenRT we can get output. So we can get what are the current. So here we can see in blue figure, we are receiving current, 3 currents, and the SOC level of all the volt. So we have 3 current, and we have also this input, which is PD. We can take is the load power also. So these are the output which we are taking out from the OpenRT. 3 currents, 3 SOCs, and value of PD. So these 7 outputs are given to this DSP based processor. So now I want to check whether balancing is happening or not. So I have to write some code. I have to develop an algorithm. What should I do with this? How should I change these currents and SOC to achieve a balancing? So I want to equally share the power. So there can be different strategies based upon which I want to design this algorithm. Let's say equal sharing is the criteria, that power should share equally among all the 3 batteries. So SOC of 3 should be same. So that logic I have to develop. So that logic I will write inside this DSP based processor. Then this, based upon that logic, the DSP has this EPWM pins. So through this pin we can get the PWM signals, and those signals we can again give back to the OpenRT. So inside OpenRT, this driving circuit. So these 3 signal D1, D2, D3 will go to this OpenRT driving circuit for each driving circuit. So from OpenRT we are taking 3 currents, 3 SOCs, and 1 PD demand. So those are in, so they will give analog output. We convert it into digital domain. Then the DSP is working in digital domain. It will convert. It will provide digital input. So OpenRT has both digital input, digital output. So since these switching pulses are digital only, so we can directly provide these D1, D2, D3 to the OpenRT's digital input, and then we can see, we can monitor all these things on this CRO or DSO. digital signal oscilloscope. So we can validate whether our control logic is working or not. So we don't have the actual battery. We are modeling them inside the Opal RT. And whatever control logic which we have developed, that also we are burning inside a DSP based processor. And then we are checking whether our algorithm is working fine or not. If it is working fine on this modeled system, because this modeling is as per the actual battery. The actual battery model is also similar to this model. So if it is working fine here, so it will work for the actual battery also. Is this clear? Is this clear? So this we have seen. What is this host PC? What is the use of this host PC? Can you tell?
For references,
Actually, the code which we are building, right? In for DSP is a processor. So we want to feed the code inside the DSP. So all these DSP, they have some software which we can run on our PCs. So on those softwares we can write these codes, and then they have this connection, right? This cable is connected to the PC. So we can dump the code written in MATLAB here onto this DSP. So the control logic is written in MATLAB in this PC, and that is dumped onto this processor, DSP processor. Is it clear? So next is the electric vehicle charging infrastructure. So in now electric vehicles are increasing, and we will see even more electric vehicle. Recently, the first hydrogen bus has also been started in India, in Delhi. They have started. IUCL is producing hydrogen. The range is around 350 kilometers. So because EV electric vehicles are increasing, so we need to develop standards for charging infrastructures. Different countries have different standards. So India has also adopted several standards. So there are 4 modes for EV charging. One is mode 1, which is direct connection to the socket. At home we have this 15 ampere circuit. We can directly connect those chargers, EV chargers. Those are simple EV chargers. We can see once. Do any one of you have e-bike or scooter, electric two-wheeler? We can directly connect those charger into our 15 ampere sockets. Those charger also like simple 3-pin or sockets. So they do not have any special safety measures or safety toolbox. So they are for small, because these two-wheelers, their charger, their converter capacity is very, maybe maximum around 3 kilowatt. Okay, but as we move to car, so these go to mode 2. So they have portable chargers. So you will see they have these the sockets which you can see here. Such type of sockets are there. I don't know whether you have seen, but in Mumbai, in Delhi, also in some complexes, in government campuses, they have these chargers. So you will find these type of uh, these charging cords. So in that they have this safety system within that cable itself. So that cable is there, and in front of that cable, these different types of these charging these slots are there in that cable itself. So they have this communication as well as safety features. So they are available in both public and domestic systems. So we can use them. So they are applicable for these cars have these. And then third one is EVSE equipment. So this is AC charger, but actually it is not on the vehicle. So the special safety feature in cable, it is called control box. So in M3 mode 3, the control box is not in the cable, it is outside. So it is outside inside an equipment which is EV, electric vehicle supply equipment, and it is permanently connected to the network or the grid. So these are wall mounted or commercial automatic charging station. So they have all these features. In that safety feature is inside those EVSC equipments. So Tesla has their wall mount feature. Even I think Hyundai Kona or something, they have also this wall mounted. Even one, I think Ola or some, they have for two wheelers they have they are providing this wall mounted is types of EVSC for two wheelers only. Maybe one or two wheelers can charge through that, and it also has that payment mechanism. You can pay whatever charge has been drawn. We can pay accordingly. So it will generate the bill also. So and next one is the fourth one, which is DC. All these are AC. All these three are AC. This is DC fast charger. This is mode 4. All the EVs they charge in DC only, because battery they take DC power. But why are we using AC? Why do we need AC chargers? Anyone? And if we can have directly DC chargers, why not have these DC fast charger on the vehicle itself? So you can get the answer from this if you see this. So can you tell the difference? We can see mode 4 is this one, right? It is directly charging the battery. But we cannot have such a huge charger on the battery, on the vehicle itself, because that will increase the weight of the vehicle, and that will also require space. Lot of space is required, and also it it will increase the weight of the vehicle, it will increase the cost of the vehicle. So we do not have big converters, onboard chargers on the vehicle. Onboard chargers are small, their capacity is small. So these are the onboard chargers. So if you want to connect to the AC system, then because battery is requires DC, so we need the AC to DC conversion. So that is done by this onboard AC charger, and its capacity is limited. Because if its capacity is more, then size will increase, it will add to cost. So this DC fast charger, which we will see just like when we go to petrol pump, we fill our vehicles within 5 minutes, right? Even we can have full tank in 5 to 10 minutes. So similarly, we want to do that type of charging. So DC fast charger can charge the vehicle within less time. So now we don't have these DC chargers right now, but government is developing this DC fast charger infrastructure, charging infrastructure, so that we can reduce the time for charging the vehicles. So these they can have a huge capacity, 2 kilowatt to 200 kilowatt. AC are only up to 22 kilowatt. That is why the vehicles, if we charge them, if we charge a Tata Nexon EV at home, it will take around 8 to 10 hours. But if we charge outside using M3, then it will take less time. But if we charge it using M4, then it will take even lesser time. So this is the architecture of EV charging system. We have electric vehicle supply equipment. So this is the EV, and then we have these three things. One is the electric vehicle, one is equipment, which is used for charging the electric vehicle, and third one is the CMS, Central Management System. The CMS it's a cloud-based system. So what the owner of the EVSC is having this CMS also, cloud management system. This cloud management system can talk to this EVSC supply equipment as well as to the users. So users can contact with CMS using these mobile apps. So the CMS is cloud-based, managed by company operating the system, and it enables the user-defined apps. So just like we book cabs on Ola, so we can have this mobile app and we can see which is the nearest charging station. And we can book slots in advance and even do payments. So that type of services are done using this CMS. Similarly, how CMS connects with EVSC. So EVSC and CMS can communicate. The CMS can know. It can communicate the charging rate. What is the existing level of how many vehicles are connected to the EVSC? How many slots are available? So it can connect the user to EVSC. So EVSC can have several slots, but how many are available? That if user wants to know, the CMS has to contact. There should be communication between EVSC and CMS. What is the discharging rate? So all these things can be controlled and monitored. And then electric vehicle and EVSC can communicate with each other for authentication, metering, payment, and remote monitoring system. So all these things are interrelated using communication infrastructure. So EVSC will connect the charger to the main supply, and the EV connects to this electric vehicle. So these are the different smart charging concepts. One is time of use tariff without automated control. Then basic controlled on and off, which is also called plug and play. So you can. So it is actually not smart. You are just anytime you can on and off. So it means charging or discharge. It's not discharging. You can charge and you can off it. You can stop charging anytime. Then this is bi-directional controlled. So bi-directional means it can. So in this we have this vehicle to grid. So vehicle can supply power to grid. So for this we need aggregator in between. One vehicle cannot provide that sufficient amount of power to have any impact on the grid, or grid cannot provide grid support services alone. So in between we need aggregator which can pool different electric vehicles to provide those grid support services. Similarly, then we have this vehicle to home. This we can even a single electric vehicle which has a capacity of, let's say, 30, or Nexon has around 42 kilowatt hour battery. So in case of emergency, the vehicle Electric vehicle, if it is connected to socket, it can supply power to the home. Emergency purposes, we can use this. Similarly, vehicle to building. So within the parking lot of a building, if there are few vehicles, they can, in emergency case, they can supply power to. They can meet the demand for critical loads using the vehicles in the parking lot. Similarly, one is this vehicle to. It should be vehicle to vehicle. One vehicle to vehicle is also there. So two vehicles can also share. So all these are very similarly. This especially this is very futuristic. Two vehicles sharing power dynamically. It's very. We need coils, proper alignment, everything. And even vehicle to vehicle can also have allow means help in several ways. We can these two vehicles can communicate. They can have safe distance between them to protect any kind of accidents. Even uh, there are several applications for this vehicle to vehicle also. Then another is dynamic pricing with automatic control. So time of use tariff without control. So we have peak and off peak pricing. So there is no control. But here dynamic pricing, we can control which electric vehicle to charge how much. So all these are different types of charging methodologies. Right now, which one we are using? Which one are we using? Can you tell? Right now, which one is being used? Right now, we use this. We charge anytime we like. We can disconnect the vehicle anytime. So then, last one is this hierarchical control of hybrid AC-DC microgrid, and this we have already covered. So that is why I have not. This is the only one or two slides on this. So different components in a hybrid. They have,
Sir, in previous slide, in bidirectional control, we are using vehicle to grid or vehicle to building. So, what is the actual meaning? Means we are charging our vehicle from grid, vehicle to grid
no.
concept. Smart.
Okay. Yes. So when we
Oh,
are charging, right? When we are charging, it is grid to vehicle. So grid is supplying power for charging the vehicle. That is G2V, grid to vehicle, which we are using right now. So we are charging. We are taking power from the grid.
and what is meaning, sir? Vehicle to building
Yeah. So
means we are taking from building or charge from building for the vehicle.
yeah, we are taking power from vehicle and using supplying some load within the building. That is vehicle to building.
Acha, acha.
Similarly,
So
vehicle.
it is similarly from building to vehicle. So it
Yes.
may be bidirectional.
Yes. 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 So
Yes.
this home to vehicle, building to vehicle, grid to vehicle, it is already in place. We use it. Even we can say this. We can say grid to vehicle will have all these three. This is same. Grid to vehicle is same for all. Anyhow, even
Yes,
home.
sir.
If we connect at home, that is also even connected to grid only. But to differentiate, because a single vehicle cannot have impact on the grid. That is why we classify them separately, vehicle to grid, vehicle to home. But a single vehicle can supply critical loads in a home.
Yes, sir.
So that is why it is classified separately. Even this is also
Sir,
vehicle to grid.
what is the main source at the charging station, sir? We are getting power at the charging station. What is the main source from the AC supply, which we are getting for industry or home? Same like that we are getting at the charging station.
Yes, yes, same.
Acha.
So also we can have these. Right now we are using the same whatever is coming, but we can also have these solar and wind hybrid plants, and then have a charging station there. Have a storage also. so we can get
Yes,
continuous
sir.
clock. So these are new projects which will be in future. Such projects will be there, where we'll be having hybrid solar, wind storage, and a charging station also.
Yes, sir.
Some charging station in UK, in Europe, uh, they have charging station, and above them they have these solar panels. So parking lots are there. They have solar panel, and one charging station is also there. One wind farm is there. So one wind turbine is there. So for a small parking lot, they can do charging. So such things are possible. No, these things are there. So these components we have seen physical, these different distributed generators, converters, AC, DC microgrids, then communication, network, technologies, protocols, standards, and structure of hybrid microgrid. This also we have seen. We'll see in the next slide. Mm. The need of storage in microgrid we have seen, because mostly we are focusing on is renewable resources as distributed generator, and these are intermittent, so we need storage. And management of power can be of two types: power or energy. Management of microgrid can be from two aspects. One is power and energy management. So for power, we try to meet the instantaneous operational conditions. So instantaneous changes. So we'll say inertial support, primary frequency control, all these things. But energy services which require, these are long duration services. So optimal demand generation balance with emphasis on desired longer term outcome. Let's say minimization of loss, minimization of cost. So all these are long term outcomes. So these are energy based management techniques. And control of class for control, we have these decentralized, centralized, and distributed. This we have already seen, but just a quick review, because these are important. You will see again and again. Centralized, we need communication, and there is central node, and there is access to global variable. But the problem is single point failure. If one point fails, then we cannot operate that PG. So it is not reliable. Then we move to the decentralized. So first is decentralized, then we go to centralized, or you can say to decentralize. We will move to decentralized. Decentralized is communication is not needed. Control is for local variable. We cannot achieve the global optima here. Global variables are inaccessible. So there is no problem of local control here, but achieving the global goal is optima is not possible here. So the hybrid of these two is the distributed. Here communication requirement is less. It is needed, but it is reduced because we need it. Uh, it emphasizes it does the peer-to-peer communication. So there is no problem of single point failure because each one is communicating with one another. If one link is broken, still we have information. So this problem is not there, and also it has access to global variables. So it's a hybrid of these two, decentralized and centralized. Let's take questions now. Purpose of bleeder resistance connected across the snubber circuit is, actually this is the DC link capacitor. So can you tell answer of this question?
A,
A, yes, correct. A is correct, to discharge the stored energy in the capacitor when inverter is not in operation. So next is this also we discussed. What is the purpose of snubber circuit which is connected in parallel with each IGBT module?
DVDT, sir.
Yes,
High DVDT.
against high dV by dt, correct. And the next is which of the following loops are there in grid connected PV generation? MPPT, inner current control, grid synchronization, all of three, or A and B. Which one?
All grid synchronization.
A and B.
And this is PLL. So now, what's the option?
Sir. All of these.
Yes,
All of the above.
correct. All of the above is
D,
correct. We need MPPT to extract the maximum power. Then we have current control loop and also PLL for grid synchronization. All of the three. Then next, select the correct option for DC link capacitor. Capacitor, it should be voltage. Capacitor voltage. So what? Which one is correct? That DC link capacitor voltage should be rated less than the peak grid voltage, equal, more than, or doesn't matter.
P. It is more than the uh,
Yes,
peak
it should
voltage.
be more than the peak grid voltage. Then only there can be power transfer from DC to AC side. Identify the correct statement with respect to solar inverter. It converts variable AC power from PV panels into fixed AC. It can operate only in grid connected mode. It cannot provide grid support services. None of the above. B and C. Which one is correct? There
None.
is none.
None of the above.
Correct.
It cannot.
So it can provide grid support services. So we can provide reactive power. It is possible. Three major factors to be determined for performing active cell balancing are, actually this we didn't discuss, but it is mentioned in lecture. I forgot to mention this.
All of the above.
Yeah, all of the above. We use this energy sharing, and this was buck boost buck converter topology and balancing strategy was also SOC. What is the full form of CHIL? This also we have discussed. Which one is correct?
Controller hardware. A, sir.
A is correct. Controller hardware in loop. Then next is which of the following is correct with this? So someone is
C.
just to,
It is C.
yes. Which of the following is correct with respect to DC fast charger? Fast charging operation is done in constant voltage mode. Is it correct? See, this we didn't discuss this. No, fast charging
No, sir.
operation.
No, sir. Voltage will drop
Yes,
actually
yes.
during fast charging.
No,
Means
fast
option
charging
will be A.
voltage will
A
increase.
will be answer, sir.
It no, it is not on board. On board, we cannot have a big charger, right? Because space is the constraint, cost is the constraint, weight is the constraint. So it is always off board. It will be outside.
Yes, sir.
So this is what
Then
about,
none of the above.
what about option B?
Thin cable for fast charging means
Yes,
cooling requirement will also be there for fast current.
correct. So this is not correct. So none of the above is correct, no? Because fast charging operation is done in constant current mode. Once the voltage SOC reaches a particular, because one of the drawback of fast charging is that SOC cannot go beyond a particular value, like maybe around 70 to 80%. Beyond that, it will not increase. So fast charging is done up to that in current control mode, and after that the power is reduced and it works in the constant voltage region, because initially constant is, we don't want to increase the current, never. So current, initially we have a constant current mode, then voltage is slowly building up. So it, once it reaches a particular value or the rated voltage, we just maintain it at that level, because now voltage is constant and power demand also we have reduced. So, So current will also reduce slowly, because as the battery goes to 100% SOC, the power requirement will reduce.
Yes, sir.
So initially it is in CC mode, then it converts into CV mode. This is for DC fast charger. These are the drawbacks for this DC fast charger. So higher current will lead to higher losses in charger and battery, which leads to degradation of capacity. Then higher C rate also reduces the battery life because of excessive heat, thermal runaway. And then fast charging, this I have already told that it can reach only up to 70% or 80%. And thicker cables are required to allow more current. The solution is to use thin cable, because thicker cable will not be flexible also. They will be, more the cable is thick, it is difficult to move them. It is not flexible. Flexibility is also compromised. So the solution is to use thin cables with some cooling mechanism, but that will increase the cost. So we have to have some trade-off between the two, cost and flexibility of the cable. So none of the above is correct. Next is, which of the following is or are advantage of smart charging? So smart charging increases the system peak load, or it increases the hosting capacity for distribution network operators, time of use tariff optimization, and demand charge management.
C, C.
Oh, not, what about A? Why not A?
Yes, sir. More hosting capacity for distribution network.
So more hosting capacity means we can have more renewables.
More renewable will be required.
We can install more renewables if we have these. We can do that, and we can charge when the vehicle solar is at peak. We can charge the vehicles, right? That way, more, if solar PV installation also increases, and during daytime when the peak solar is there, we can charge the vehicles. So that is one of the smart charging. So if generation is more, charge the vehicles, because at that time, if generation is excess, the price will also be low, right? So both A and C are correct here. It will not increase the system peak load, because if we are using smart charging, what is the use of smart charging if we are increasing the load? So we will try to shift the load. We have seen these, peak valley filling, peak shifting. We will try to shift the peak by using these smart charging strategies. Select the correct option with respect to the importance of energy storage in microgrid. Energy storage are critical to enable standalone operation of microgrid. Energy storages smooth the microgrid power during grid connected operation. Both A and B or none?
B, sir.
Why D?
B, B, B.
Oh, B.
Smooth the microgrid power.
And why not A?
Critical to enable standalone operation. Standalone operation.
So
Yes,
A,
sir. It will also enable standalone operation, but critical to enable. Yes,
because
sir.
when we talk about microgrid, we talk about renewables. So if a standalone renewable microgrid is there, renewables are more, and it is not connected to grid. So what will happen when the renewables are not there? So how are we going to meet the demand in that case?
Yes, sir. Both will be.
We need storage, right? Without storage, we'll not be able to meet the demand when the solar is not there or wind is not blowing. So energy storage is very important in isolated or even remote microgrids. So is answer. Okay, so these are two types of energy storage: capacity oriented and excess oriented. These are two classifications. So as we can, from name only we can say capacity oriented means we need high power density for these type of energy storages, right? So hmm, there's not high power, high energy. So we need high capacity from them, high energy density. And this access oriented means they should give fast, quick access. So for them we need high power density. So they can, their response is fast. They have fast response. They can respond to short-term disturbances such as they can provide inertial support for primary frequency response. So flywheel, supercapacitor, and this supermagnetic conducting device, energy storage. These can provide these access-oriented services. And then capacity-oriented energy storage are the slow responding energy storage, and they can help in long-term energy balance or power balance, and they can they can provide the tertiary frequency response, secondary frequency response, and also they can smoothen the output of renewable generation generators. So all the other storages will come here: compressed air, pumped hydro. Now hydrogen is picking up, so government has a lot of focus on hydrogen. So with this, yeah, both A and B was correct for this. So select the possible configuration for hybrid AC-DC microgrid. We didn't discuss this one. Then it will come in the next slide. Yeah, so which one is correct for this? AC coupled hybrid microgrid, DC coupled, or AC-DC coupled, or none of the above.
C,
So
C is answer.
select the possible configuration. So here multiple choice. This is multiple choice.
Then ABC, all are correct.
It's correct. ABC is correct. So this is the difference. So AC coupled means all the generation and load is connected to this AC bus. Here they will be connected to DC bus, and here we'll be having both AC and DC bus. Here we'll be having AC bus, DC bus, and in between we will be having these DC to AC converters. So here what is happening, DGs and SCs or energy storage are connected to common AC bus through the interlinking converters. And then DC coupled, they are connected to common DC bus. And then interlinking converter is used to link the DC and AC buses. And then in AC-DC, they are connected to DC and AC buses. And buses are linked by these converters. Sorry, this is interfacing converter, not interlinking. Interfacing converter, and this is interlinking converters. Okay. So yes, ABC is correct. Which of the following is not true about interlinking interfacing converters? This also we didn't discuss, but it was there in the. There are two types of interfacing converter. One is interlinking converter, another is back-to-back converters. And three-phase inverters are example of this. Interlinking converters. So which is not true about them? Which one is not correct here?
Inter B.
B is correct. A is
It is D. D is not correct.
so we can see here. So you're saying B is not correct. So these are interlinking converter. Single stage three phase inverter is an interlinking converter. These are bidirectional and they work on this principle. Equalizing DC side per unit voltage and AC side per unit frequency. And back-to-back converter are, this is one type, dual stage converter with three phase inverter. So we call, just as in HVDC we have back-to-back converters, right? Back-to-back HVDC. So in one station we have two converters. That is why, so grid side, the rotor side converter, grid side converter is, it's an example. In DFIG, this is an example of back-to-back converter. So these are dual stage converters. So in PV also, if we have these two, DC-DC and then DC to AC, these are back-to-back converter with three-phase inverters. If single stage three-phase inverter, it's an interlinking converter. Just as here we have, if we have the AC bus, we have DC bus and AC bus, then we can have this DC to AC converter, single stage and bidirectional. Okay, so this was correct. Back